Welcome to ThirdEye Labs, where we make the unseen seen. Today, the geometry of tensors. The word tensor did not come from computers. It was born around 1900 in a branch of math called tensor calculus, built to describe stress inside a material and the curvature of space. Einstein then used it as the language of general relativity, the math of curved spacetime. And in 2015, when Google built its machine learning engine, it reached back for that same word and called it TensorFlow. A 120-year-old idea about the shape of space became the container for all of modern AI. And the word itself is a clue. Tensor comes from the Latin tensus, meaning to stretch. In physics, it measured the stretching and stress inside a solid pulled under pressure. Hold on to that picture, stretching, because it is exactly what a neural network will do to data. Most people picture data as a flat spreadsheet, but math has a whole ladder of shapes. A single number is a scalar, a point. A row of numbers is a vector. A grid of numbers is a matrix, a sheet. Each step adds one dimension. Add one more dimension and the sheet becomes a stack, a volume. That is a tensor. A color image is 3 stacked sheets, one each for red, green, and blue. Its shape is 3 by height by width. Stack frames over time and you get a video. Add a batch of examples and you have a 5-dimensional box. The shape is just the dimensions of the box. A quick honesty note. In physics, a true tensor must obey strict rules when you rotate the axes, the laws of covariance. So why do we get to ignore them? Because in deep learning the axes never move. Channel 1 is always channel 1, pixel 1 is always pixel 1. With a fixed coordinate system, those physics laws simply drop out, and the tensor collapses into a plain multidimensional array. We only have to remember them again in Act 5, when the grid itself starts to bend. Still, an AI tensor is more than a NumPy array. It remembers how it was made, keeping a link back through every step that built it. So when the answer is wrong, the error can flow backward along that same path, a gradient returning home to fix the weights. A tensor that remembers its own history. That memory is exactly what lets a network learn. How does a volume fit through a flat layer? You reshape it. Watch a 3x3x3 cube unroll into a single line. And here is why that is almost free. On top, the shape we see. On the bottom, the real memory, one flat strip of numbers that never moves. Reshape from 2x3 to 3x2, and only the top regroups. The strip stays put. All that changed is the strides, the jump sizes we use to step through the very same bytes. But free does not mean harmless. When you flatten an image into a long line, the bytes survive, but the geometry does not. 2 pixels that were touching are now far apart in the line. That lost neighborhood is exactly why convolutional networks and vision transformers refuse to fully flatten. They keep the grid, or cut it into patches, so near in space stays near in the tensor. So what does a layer actually do to the box? The core operation is a contraction. Y equals W times X sums over a shared axis to collapse 2 tensors into one. Geometrically, a linear layer bends space itself. Watch a single matrix warp the entire plane. The grid lines stretch, and the 2 basis arrows move. And the shorthand for this sum has a beautiful secret. It is called einsum, short for Einstein summation, the exact notation Einstein invented for relativity. The same idea that described curved spacetime now writes every layer of a network. With real numbers, this W stretches the first axis by 2 and squashes the second by a half. The point 1 becomes 2, 1/2. Then comes the fold. The most common activation, called ReLU, takes the straight line and creases it. Everything below 0 snaps flat to 0. It is an origami fold in space, a sharp crease at the origin. Smoother versions, like ReLU, round that crease into a gentle curve. Stack thousands of these folds, and a network can carve space into almost any shape. Here is the heart of it. 2 classes of points, an inner ring and an outer ring. In this flat plane, no straight line can ever separate them. Try, and you always cut through both. But a network can warp the space. Lift every point by its distance from the center and watch. The inner ring stays low, the outer ring rises into a bowl. Now a single flat plane slides between them. What was tangled in 2 dimensions is cleanly separable in 3. Meaning became position. That is what every hidden layer is doing, folding space until the answer is a straight cut. Once you see it, tensors are everywhere. A convolutional network turns one image into a tall stack of feature maps, each sheet hunting a different pattern. Edges, colors, textures, then whole objects, layer by layer. A transformer's attention is just a tokens by tokens grid, a heat map of who looks at whom. But that grid grows with the square of the length, so sparse attention keeps only the cells that matter, a mostly empty map. That is the trick that lets context windows reach millions of tokens. And it reaches all the way down to the silicon. The chip reads memory in contiguous chunks called cache lines. If you store all the reds, then all the greens, then all the blues, one pixel's 3 colors are scattered far apart, so the processor must leap across giant strides to gather them. Flip to channels last, and a single pixel's colors sit side by side, in one cache line. Layout is just the act of aligning our geometry with the physical pipeline. Add a time axis for video, and a batch axis for many examples, and the same rules carry all the way up. So where does this go next? The whole frontier comes down to 2 moves, changing the canvas and changing the flow. First, change the canvas. Not all data lives on a neat grid. Geometric deep learning puts tensors on graphs, like molecules and social networks, on spheres, like the globe, and even in curved hyperbolic space, which fits trees and hierarchies with almost no distortion. The grid we locked back in Act 2 is finally allowed to bend. Second, change the flow. Instead of stepping through a stack of fixed, discrete layers, continuous time models, like neural differential equations and liquid networks, let the tensor flow smoothly down a pipeline, its dynamics adapting to the input. And physics-aware networks bake symmetry straight into that flow, so a molecule is understood the same no matter how it is turned. So here is the whole journey in one breath. Data is not a table, it is a volume. A neural network bends that volume's geometry, fold after fold, until meaning becomes position. Learn to see the shapes, and abstract code turns into tangible architecture. Next time, when the grid itself bends graphs, spheres, and curved spaces, where tomorrow's networks will live. Thanks for watching and keep exploring. Next time, beyond the grid, please like and subscribe ThirdEye Labs if you enjoyed this video and let me know in the comments.